Hi everybody. Hope yes, you will enjoy this. I will give you a little bit, kind of an overbit of a view of sustainable development to begin with, and then I'll kind of say I'll look at it from an engineering point of view, how engineers can contribute to working towards sustainability, and what are they involved in, and so on. And what's smattering with a few of the research projects that we've been doing, just to kind of highlight some of the things that engineers can do. So I hopefully you'll like it, and hopefully it'll be informative. And I don't want to get into too heavy stuff, but anyway, you can ask me any questions, of course, at the very end. So I don't know how well this works. Okay, so basically we're looking at sustainable development. Probably everybody's heard the definition, so really just to get you onto it. So from the Brundtland Commission, basically people are saying that we want to be able to have development. So in terms of, especially that's what engineers do, right? They develop things, bridges, roads, whatever. So we want to be able to meet the needs of the present, but hold a few things for the future generations, for the kids and things like this into the future. So this is basically, so you have to be able to do things in a really well-planned way, which really hasn't been done in the past. And people are starting to realize that you need to do that. So in 1992, you had the summit of Rio. It contained a number of environmental and economic aspects, the social aspects, and so on. Unfortunately, it's not binding, so it doesn't, people don't have to follow it. But then, of course, we look at the climate change conference, and people have not really followed that either. So, but at least it gives a little bit more incentive if there's some kind of reward, I guess, to going to ISIS. So basically, they said that we want to be able to achieve sustainable development and get a higher quality of life, but we have to reduce what we're using. We have to reduce the production, the consumption, and the demographics. So there's obviously a lot of the society aspects, but also some of the products that we are producing as well. So all of this is really, really got to be integrated. So what they did was they came up with 5 priority areas. And I think in particular for the engineering, we look at the engineers are highly involved in 2 of them in particular, the water and sanitation and the energy aspects. The health is more of an indirect, because obviously if you have less pollution, you're going to have better health. If you have, the agriculture, again, we have the agricultural engineers, but again, maybe a little bit less. So there's some, and the biodiversity, again, is a little bit more indirect as well, in that you have the people, like if you don't destroy the forest, obviously there's still some things that are left in the forest in terms of the butterflies, as was being mentioned, and so on. So these were some of the objectives that were looked at in terms of the water and sanitation. You want to be able to have the portion of people that were accessed without sanitation. So this is I forget exactly what the proportion is right now, but it is still not getting anywhere, and I don't think this is improving to any extent. So you have especially countries like in continents like Africa, of course, there are many, many places that don't have good access to water. You have countries like India where people are still bathing in the rivers and things like this, and hauling water in various long distances and so on. So this is still a substantial problem. Energy, we have to look at alternative energy sources. Of course, we're using the oil and so on. How do we look at other alternate sources of energy, and how can we increase the efficiency? So obviously, if we burn less, we have more left for the future. For the health aspects, we can look at what kind of chemicals are used. Actually, I think that there are being significant advancements made here, where they are looking at reducing some of these the fluorine container gases, where you have all these spray things. They've looked at using different chemicals that have less effect on the ozone layer and things like this. So there have been significant advances there. However, in some countries, obviously, like if you go to Beijing, which I've been to, you can hardly see across the street. So the air pollution in these countries, and of course then the effects on the respiratory effects and things like this are quite significant. So the biodiversity, we have many problems with some of the fish stocks and things like this now. So this is obviously a trend that's occurring more and more. Like we have the codfish out the Atlantic Ocean there, which is severely depleted and things like this. So these ones are quite problematic, and of course we want to be able to work towards repopulating and restoring some of these fisheries here, because obviously it has the impacts on the humans in terms of their what types of foods, but also in terms of the jobs and employment and so on. And in the agricultural, there are many, the land is, I think it's something that's really undervalued in terms of people think of water, 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 but the land is also something that we really need to keep track of, because if we don't have sufficient earth to be able to grow the food, how are we going to be able to grow the food? So, so we have losses through wind, through runoff of heavy rains and things like this. Like all of these variations in the water supplies in terms of the really heavy rains can carry away a lot of soil and so on. You have all of the things that are the coastal erosions and things like this. So these are all having significant effects. And so these are things that we have to think about for the future. So as I was saying, pollution is obviously one of the major aspects. So we have my urbanization is a little bit faint there, but the industrialization, urbanization, the agricultural industries, they all produce various waste streams. So we've done various things to be able to develop processes to treat them. But we have to look at it a little bit more, how do we prevent some of these waste streams in the beginning. We have the resource exploitation. Of course, people have heard about the oil sands and so on, the different emissions that's being produced, the effects on the water, the river, the depletion of the rivers around the oil sands, things like this. So these also have specific, and especially the tailings, which are basically what's left over from the extraction processes. So almost any mining industry, that's exactly what's left over, these tailings. They do the extraction for your copper, zinc, lead, oil, whatever, and then whatever's left over is what they stockpile. And normally there's going to be some kind of leaching of these materials, and it can go into the groundwater, it can go into your rivers and lakes and things like this. So things like acid mine drainage, basically, which is a biological phenomena, production of acids, which then enhance the metals that go into the rivers and lakes. So the agricultural industry, you have a lot of fertilizers that add. So then if you add to excess fertilizers, then these fertilizers in the form of nitrogens and phosphorus will go into your rivers and your lakes and then cause all sorts of problems, like probably we heard of maybe a while ago, that's blue-green algae problems and things like this. It's less, we hear about it less, but it's not, just because we hear about it less doesn't mean it's no longer a problem. It just means that the press is not interested anymore and they run off and find something else. So, and then of course the forestry, we keep cutting down the trees, which are a natural sink for our carbon dioxide. And and also that has an effect on, if you don't have the roots from the trees and so on, then you're going to have the runoff and the loss of the good soil and things like that. So all of these, in some ways can contribute to pollution, which can get into your groundwaters, which then can have certain effects on humans. So these are kind of the graphic that will show what are some of the effects on humans, or how we can be exposed to various pollutants. So if you have contaminated land, it rains and so on, which then allows the pollution to go into the groundwaters, which will be further down. You can have all of these little streams here. I don't know why this one is green. It must be impacted by the nitrogen and phosphorus. It was blue at one point. So you have these streams which people drink, obviously, or fish or things like this. So then it can be by direct contact or ingestion, could be exposed to various contaminants. You can have, as I was saying, the plants. So if you're growing something that's in a contaminated area, the plants will also extract out some of the contaminants as well. And if we eat those, then we can be exposed to that. Certain compounds are volatile, so they'll go into the air. So things like various gasolines and things like this really are very volatile. They'll go into the atmosphere, it rains, and then it can be redeposited somewhere else, for example. Or you could be just by inhaling these type of compounds as well. So these are some of the different types of exposures that we can be subjected to. So these are just for some of the, obviously the various health effects of different things. I don't want to go into these too much, but just so in terms of kidney effects or various cancers or effects on skin conditions, things like this, nervous and toxicity effects. Arsenic in particular is actually almost like a natural contaminant. Actually, in some countries like Bangladesh and in India, in East India, you have people drinking water that's naturally contaminated by the arsenic. People are not really sure why it's been getting into the groundwater and so on, but this is what's happening, and people are having all of these skin lesions and problems with their nervous system and things like this. So this is a huge problem, which is actually a natural effect of different chemicals as well. So not only do humans put things into the thing there, these things can happen as well. So getting to more the engineering background. So we are producing all of these different wastes, pollution, and so on. They cause various health effects. We're also depleting the resources as well. We can't, something that we take through the mining industry, we can't stick back in. It won't grow or anything like this. So once it's out, it's out. So there obviously will be a finite resource that we'll have, and eventually we will run out of certain things. So these are the things that we need to take care of. We have the degradation of the ecosystems. We're removing so many wetlands and things like this that were naturally there to be able to build our cities and things like this. So these are all the things that we've been doing. So either engineering sometimes leads to these problems, obviously, and hopefully we can use engineering to solve some of these problems as well, and particularly related to water and energy resources. And then hopefully this will help us to work a bit more towards the sustainable development, what we're trying to do, which is obviously the aim is, to, as you remember, to save some of these resources for future generations. So this is all the population growth, the industrial problems, and so on. We have these non-renewable resources and all this environmental degradation. So these are things that are obviously quite problematic, leading to problems of food pollutions. We're probably starting to see areas also where they might even get into wars over water. Even in California region, sometimes there's a lot of depleted areas where there's not much water, so they want in Canada to be able to ship them some water through various pipelines and so on. So these ones, of course, are, we're friendly countries, but you can imagine if there are two countries that don't get along very well, that this could be getting quite problematic. So anyway, that's pretty much the same type of thing. Basically, we're saying, okay, we have to look at this we have to look at all of the things that we need for the humans, and then we need to look at the various ecosystems in terms of the environment. And of course, we need to look at the social and economic aspects as well. So this is the other aspect, of course, that we have to consider when we're looking at. So how does certain developments impact, say, for example, if we're doing a mining project up north, you have to consider the Aboriginal cultures and so on that are living in that area. So you have to consult with them and so on. So these are the various social aspects that you have to look at. And of course, anything that we do, you have to look at the economic aspects, of course, because things, different things cost the different money and things like this, and they'll have aspects of jobs and all of these other, over the long run, how much things will cost. So, I mean, in the past, people have just kind of looked at, okay, this is A, B, C, this is one's more expensive than the other, so we're going to tend to go with the cheaper option and then we'll run with it. But maybe in the long run, it's not necessarily the cheaper option. Maybe there's certain things that we're going to be needing over time, and so maybe it causes much more maintenance or whatever, so maybe over the long run, it might cause a lot of difficulties. So anyway, so basically that's sort of what we're saying. How can we reduce these non-renewable, this depletion of these non-renewable resources in particular? So these pollution problems is definitely within the purview of what the engineers have to do. Population, well, our own family, maybe we can do something about, not have 10 kids. But other than that, it's not really part of our engineering community and what we have to do. But the food production, in terms of how we manage the waste, the products, the waste streams, how we remediate the polluted lands, and then how we do all of this is definitely things that the engineers can be able to look at. And of course, this depletion of the non-renewable resources, how do we look at it, and then relate it also to the socio-economic aspects as well. Okay. Oops, I guess it's just because. So we have the tools, we have the way, we have to prepare, and those are just basically some of the follow-ups to what I was just saying anyway. So basically we don't need to consider. So one of the things that we can look at is actually, as engineers, we can start to think a little bit like nature does. We want to be able to look at really the cycles of life. If you're starting to have certain plants or certain whatever, you have a certain source of your sunlight, you have the photosynthesis, you have the plants growing, you have the plants are eaten by the herbivores, the herbivores are then eaten by the carnivores, and then you have a certain amount of waste, and then often the wastes are deposited in the forest and so on, and then used for the nutrients and things like this to be able to grow your plants again. So basically you have roughly a closed cycle as much as possible. And so this is what we really need to be able to do things like that, you know? So if we're gonna use something, let's try to be able to use reduce the amount of waste that we're producing and try to keep this closed system almost of a total recycling of all the materials as much as possible. So maybe this is something that we need to think of and try to adapt these type of processes. So some of the conditions, I guess, for sustainability. Sustainability is kind of, as we say, it's a thing that will have stuff forever for the future, but I mean, in a way, it's not a realistic goal, but at least we can try to work towards it as much as possible and try to make it as realistic as possible. So what are some of the objectives that we need to do? We need to look at things that are renewable. So, you know, so if you use things that are renewable, then it makes it easier, obviously, to reuse things as much as possible, whether it can be recycled, whether it come from a natural source to begin with, and you can regrow it again later on. You know, these type of things make it easy. Using non-renewable resources is obviously very problematic because, as we say, once you take them out, you can't put them back in. So at least you have to try to replace them as much as possible. There's certain cases, obviously, where you don't have choices because you don't have, say, for example, we're using wind energy and there's no wind. So you have no choice but to have non-renewable sources. But at least try to use them as well as possible in as efficiently as possible. And then the emissions for pollution. You know, make sure that we're not going to put anything into the environment more than is capable to be converted. So, like, there's certain chemicals, say, for example, once they're ejected into the environment, they can be degraded by the sun and so on. So, but once you bypass this amount, like what is being done, say, for example, for carbon dioxide emissions, we can't get back to, so the levels just keep on accumulating and accumulating, right? So these are the things. So basically we need to keep into account what's going on in nature and how fast things are gotten rid of. So if you keep on accumulating more than is being degraded, then obviously you're going to start to have an increase of an accumulation of those particular chemicals, so for example. So just to go now a little bit more what some of the things that engineers can be doing. So we are looking at it in many steps. There are obviously engineers are used for building cars, they're doing computers. When I went to school, I'm ashamed to admit we didn't have computers. We didn't have all of these iPods and iPads and everything like this. I typed my master's thesis by a typewriter. So not that ancient either. So anyway, so things are obviously, we've been doing a lot of developments in the last few years. You know, so we're all, I mean, this is obviously engineers that have done all of these things. We've changed all sorts of land uses. We're obviously a much more urban communities now than we were. I mean, we used to be a very agricultural setup and so on. So now there are very few small farms, and now it's basically these agglomerates that are using very high production processes and so on. So things have changed quite extensively. We have many more cars, obviously, than were there before and many years ago, and so on. So anyway, these are what engineers have been doing. We do all sorts of water treatment facilities. We look at we do things obviously to mitigate these air and water pollutions and so on. So basically environmental engineers, that's what they do. They look after how do you treat a certain pollution that gets into the air, and then on a regular basis, how do you develop systems so that they won't get into the air in the first place. So, stop it right at the emissions for the plant and so on. So this is just some pictures from a water treatment facility from a pulp and paper plant. So the pulp and paper, basically, they use a lot of water. They used to use a lot of chlorine chemicals and things like this that were exceedingly bad for the environment. They've replaced some of the chemicals now that are used. So these are some of the things that have been done there. They still use a lot of water in the pulp and paper industry, but they've tried to reuse it within the plant as much as possible and recycle it within the plant as much as possible. So obviously you need less of the what we call the touch from the river and so on. They have to be, these plants are built on the river because they use a lot of water. And so anyway, they try to reduce as much as possible and try to reuse as much as possible the water within the particular plants. But they have these huge facilities. I forget, it's something like 50,000 cubic meters per day of water they're producing of wastewater. And so they have to go through basically these set of tanks. They're aerobic tanks and so on. And so being in aerobic processes, you're adding air to it. Then they produce a lot of sludge. And so this is basically the sludge that's at the bottom of the tank. So these type of systems, what we call sequencing batch reactors, they're basically a type of system where it's filled up with the water. You have the sludge on the bottom, you do the mixing, you do the reaction, and then once the reaction is done, you just remove the water and the sludge stays in the tank. So this way they can reuse the sludge as much as possible with as little other equipment as possible, really. So it's anyway, this I think this is basically what the water looks like directly from the plant. It's quite a bit better at the other end, but it's not perfect. It still has a little bit of color and so on. So color is definitely one of the impacts that the effluents from the pulp and paper plants have. This here is just basically the facility for removing solids. So what they do is they sediment. This is just a settling tank. The solids are settled, and they take out the solids, and they're basically a lot of fibrous stuff from the pulp and paper processes to begin with. So what they try to do is they try to use them and reuse them. They send it to other industries and so on that can reuse them. They try to use them sometimes as in agricultural, also just to mix it with some of the soils and things like this to give it a bit of porosity and things like this. So they try to use these solids as much as possible. So these are some things. So engineers also, obviously, they work at doing the extractions for the oil sands. There's a lot of, obviously, negative press about the oil sands industries and so on. Some companies are doing much better than others, and some of them realize that they really have to do more, and there needs to be a lot of development in how to reuse these waters and things like this in particular for the oil sands so that they're extracting less water. So right now they do reuse 90% of the water within their processes right now. So they're doing, they're much better than they used to be, but they still can, obviously be much better because they're still using 10% from the river. So there definitely needs to be some extra values that need to be done, but it will keep working. So these are some of the things that engineers can work on, how to improve their processes, how to get more oil out of their tailings, and then if you have these tailings with less oil to begin with, then if you store them somewhere else, they'll be less problematic as well. So these are the things that we need to look at. So obviously we're problem solvers for engineering processes. We want to look at various, we need to look at innovative approaches because and then obviously need to analyze the costs, as I mentioned, like over the lifetime of the project, not just at the beginning, not just for the equipment that's needed, but included, right from the beginning of the project right till the end. And you always have to look at the environmental impacts all the way along. And we have to consider also the political and cultural and sociological aspects as well, which is what engineers were not having to do before. Before, the engineer would just work in his little a little box basically and say, okay, I work on the process, we have to develop the process, we work on the paper and so on. But now engineers have to be much more, they have to be able to communicate with the public. They got to be able to sell their process to the public. Got to be able to discuss with the project, find out what their concerns are, so then they can incorporate them properly into their process. So it's a very different type of engineering that from before to what we need now. Okay. So basically, we can do and should play an important role. We should also play an important role with the government too, because engineers tend to keep to themselves. We need to help to try to influence also the policies of the government as well in certain areas, like what the government has been doing to some extent now, cutting down some of the requirements from these environmental impact assessments and things like this, which are definitely not the way to go. I mean, to them they say, okay, it's facilitating the process, but in the long run, that's probably not the best way to be doing things. Okay, so anyway, we need to look at these type of things to support this sustainable development. How do we reduce the resources? So just as an example of some of the things that engineers can do also for helping sustainable development, we can look at countries like Germany, especially in Europe. I think that their populations are very tight and there's not much land available and so on. So in countries like Germany and the Netherlands and so on, they've made a lot of efforts to look at more sustainable ways of dealing with waste, and look at more sustainable ways of doing things. And so, for example, for their computers, they design them right from the beginning to make sure that they can be recycled in the future. And the same thing with some of their cars, not all of their cars, but some of their cars. So you be able to build the computers properly so that when you can bring them back and then you can make them into a new model instead of having to start from scratch and using all of these very precious metals that make up the computers and their boards and things like this. So this obviously will reduce the impact because now you don't have to keep on extracting the minerals out and these precious minerals out in of the environment anymore, and it reduces quite a bit the impact. You can save money to a lot of extent because now you've used a lot of energy already to do the processing of these things, and so on. So engineers, as we're saying, they involved with what type of materials are used, how they do the processing, and then how the energies are used in the processes as well. So this is a little bit what this life cycle approach is what I meant. So not only looking at in terms of the costs of the process, overall, but also looking at the impacts all the way along as well. So anytime you build anything, you have to extract a certain amount of resources. You have to make some metals, you have to make some oil, maybe to make the polymers, and all of these type of things. So obviously you need to put in energies at this point. You need to put in water, you need to put other resources and so on. Then what you'll do, of course, once you get the materials, then you go to probably a different plant or whatever, then you'll do the modification of these processes and develop all of these processes. So trying to form it into maybe some sheet metal or so on, like doing the metal processing and things like this. The next thing you'll do is probably transport it to what you're actually building. So say, for example, you're building a car. So you get all the bits and pieces there, then you'll start molding them into the actual parts that you want. And then you have to bring it there, and then you'll do the assembly. And then finally you will actually once it's all assembled and so on, and you get it from the store and so on, then you're actually going to be using it. So this is what we mean by the life cycle approach, okay? The whole life cycle of something, of the product, of a process, of whatever. And then of course once you're finished with it, which this graphic doesn't quite include the best of it, but when you're finished with it, you want to be able to, instead of just scrapping it, sending it to a yard somewhere or a landfill or whatever, the best thing is to find a good use for at least the different parts of it, if you can dismantle it and reuse it into another car or something like this, So as we're saying before for the IBM, this is right from the beginning like that. So this is the life cycle approach. And so now you need to be able to determine what, not just your particular product, but over the life cycle, what is the impacts of that particular product have on the whole process. So And so you can have all of the impacts in terms of the emissions, the water uses, the water impacts, everything all the way through. So you need to be able to balance out everything over the whole life cycle. So things, as I was saying, like the resource, so just to break it down a little bit, we have the resources, so things like the mining industries, the extracting of the oil, extraction of water for uses for electricity, agricultural purposes, managing forests, looking at fish farms, land planning, and things like this. So this is what we're talking about in terms of the resources and uses of the resources and so on. So obviously in the oil rigs, you know, I mean, you're using all of these ones out in the ocean. You have the fish management and the fish cultures now. Basically you can, you know, build, farm your fishes now and things like that. Okay, so we can look at how in the processing, modifying of the resources, which would be the next step. Basically, you'll be going to be looking at what kinds of pollutions that are generated through all of the instrumentations and so on. We can develop the instrumentation to monitor. So there have been a lot of really good, actually that's just one of the things that's really spurred on the environmental industries and remediation processes, because now we can actually detect at very low levels what kind of materials there are in the environment. Because before, if we couldn't measure them, you can't do anything about it, you can't regulate it, you have no way to saying, well, you can't say that, oh, okay, we want only 1 parts per billion of a particular compound if we don't know how to measure it, or we can't measure it, or something like this. So there's been a lot of advances since the 70s in particular, of the different analysis techniques. So like I'm getting what we call an ICP-MS, which can measure different forms of arsenic, and we can measure down to like 1 part per billion of the arsenic with no problem. And so, but the regulations are something like 10 parts per billion or something like this, you know. So maybe once you get better measurements and better ways to actually do the treatments, then it'll be the levels of arsenic acceptable will actually be decreased. And then you can use the regulations to decrease. You can decrease the regulations. Before it used to be 50 parts per billion. So things like that. So yeah, you have all of the different industrial processes. I was saying, look at the life cycle, designing the materials, the packaging. I mean, obviously, sometimes the packaging in some places is actually worse than the actual product, because all of the wraps and the plastic around it and all of the individual wrappings and so on. I spent a year in sabbatical in Japan, and they're like, everything is absolutely gorgeous and everything is absolutely beautifully wrapped. But oh my God, all of the waste, I think, of all the materials that are used just for wrapping all of this stuff, you know, it's just like amazing. You know, so I think the packaging is another materials too. I mean, now we've gone from shopping bags to have these reusable to these reusable shopping bags. I mean, this is obviously one of the things in terms of the packaging we've gone to. One thing that's done is not done too much, but it's done in some areas, is what we call these eco parks. And basically what that means is that you have certain industries that are grouped together in a certain place. They're not very far apart from each other. And so sometimes they can coordinate. So this one might generate a certain waste, but it can be used in a process for another one. So like say, for example, another one, one place might be generating a lot of carbon dioxide. The other one, you can then capture the carbon dioxide, repressurize it, and another company can use it, say, for you know, some of the other industries in that particular area. Yeah, yeah. Yeah, these type of things, you know. So all the different solvents, sometimes they can use they can exchange reuse solvents and things like this. So this is some things that is not often done, but it's possible as well. And you know, just using industrial sites. So there are a lot of what we call brownfield sites, and they quite often that they are used by a specific company. They dump all sorts of waste on it. People don't know what's there, and then they go and disappear into the night one night, and then it's left all of this contaminated land. And so then you have to be able to regenerate it and do the decontamination so that you can use it for something else. So obviously using it for something else is beneficial for many ways, because then you can start getting taxes from the land. So economically it's a good thing. You're not wasting, going further out and then making more urban sprawl. And so you're using the land that's already there and all of these type of things. So, but obviously these type of things cost a lot of money to do the decontamination, but they really should be done, and there should be various incentives for these type of things. Those are just some of the tailings and the different debris and things like this from a tin mine. So people, a lot of the mines are far away from urban, so people don't think about them too much, but they are near usually some various Aboriginal cultures, so it can affect their communities. And now things are actually, with all of the warming and the further, probably people will start moving a little bit further north now, because it's not, the conditions are not being as severe as they used to be, so. And they have, like, the Quebec government has this Plan Nord for developing the north. I don't know how far this will go now with a new government, because that's always the problem with going from one government to the other government. So plans change. One priority of one government is not necessarily the priority of another. But obviously the development of, we have diamond mines, we have gold mines, we have the hydroelectric. So we have a lot of potential industries that could be even more exploited up north in Quebec, and we'll see what happens there. But it has to be done, obviously, in a very sustainable way. So the mining industries in particular. Actually, the mining industries, what they have to do now is they have to do a sustainable development plan. So they have to prove, if they're going to open a new mine, they're going to have to prove what their shutdown is going to look like before they even start doing the thing. So they basically have to be able to, because there will be a point, obviously, where they run out of the minerals that they're, or the diamonds or whatever that is being mined. There'll be a point where they have to close. So they have to show what is their closing strategy going to look like. Is it going to have any impact on the migration patterns? Just the mine itself will have any impact of the migration patterns of the biota around it? Is it going to have any problems with the, is it going to look like an eyesore? It cannot look like an eyesore. They have to prove that it's going to go back as much as possible to the original state. So obviously the people have, made a big hole and whatever, but they have to be able to make it so that it's as acceptable and as aesthetically acceptable, as functionally acceptable as possible. So they have to prove that what it's going to look like before they even start doing anything. Otherwise, they will not get the approvals to be able to do the mine. And of course, all the other aspects in terms of their environmental impact assessment, all through the various stages of their lives, they have to show what will happen as well. So not only when they're just starting, when they're doing the extracting, when they're doing the shutdown, and when it's closed. So they have to prove right through the whole life cycle of what they're doing now. And of course, you have to look at all of the aspects, the social aspects, how it's going to affect the community there, and so on. So these are the things that have to be done. So basically, engineers, they do a lot of work on these. You have all the recycling, you have all of the waste management, the collection facilities, maybe some not necessarily engineering companies, but basically they can design the actual landfills, so they're proper landfills. Okay. And also there's being much more effort, say for example, for using asphalt on the road. There you can reuse various like fly ashes and things like this. You can combine waste materials like waste concretes and things like this into the road material now. So they do a lot of testing of these different type of materials, and they test out the materials. They can run little pilot studies, go test. Sometimes you might see if you're driving along that this is a test area. They've written out saying that, and you see all sorts of different things. So that's what they're doing, probably looking at different types of materials. So that way you can reduce the amount of pure virgin materials that they're using to build these roads. Yeah. So looking at the various organic wastes, and of course, and looking at ways to reuse and remanufacture products and things like this. So this is a closed landfill in Mississauga. So you could never tell that was a landfill. It's obviously a golf course now. So those are the type of things that you need to be able to do in the closer, just kind of like what I was talking about for the mining. You need to be able to, like as a good closer, have a good reuse for the place. So you obviously cannot build houses and things like this on a landfill because you're still going to be having a certain amount of degradation. So there's going to be a certain amount of settling and things like this still going on. So heavy things are on a landfill, and it's an old landfill or a no-no. Also, you have the potential for some gases still to be produced. So we have the anaerobic degradation. So you have a methane gas that's being produced in the anaerobic processes. So you don't want to have methane gas accumulating in your house, and then potentially somebody just light up something, and then your whole house is going to go kaboom. So that's definitely not desirable. So this is what, unfortunately, for some of the smaller landfills, these practices are not done, where you extract the biogas as much as possible. In the East End, when it was operating, and actually I think they still are, they're still extracting the gas from the landfill in the Saint-Michel complex there. And they used to be able to generate as much electricity for 30,000 homes there in the area for the landfill. But now it's probably much less there because they're not inputting as much garbage, because once you don't put the garbage, you don't have the carbon source, and therefore your gas starts decreasing. So this is basically, they have a whole set of liners on top of the gas, the landfill, to make sure that there's no gas escaping. So obviously methane gas is a greenhouse gas, so you don't want to be able to have issues with the leaking of the gas. And obviously the more gas that you can recuperate, the more you can use for energy processes. So basically this is like a steam generator that's that can then produce the electricity for the gas itself afterwards. So that's obviously the best scenario in terms of the larger facilities in particular. This is not a good practice of, this is actually what they call it. This is basically a dump. Anything that's not landfill and is not an engineered landfill is basically a dump. And I don't know, you can see this is basically probably a 30-year-old landfill. You can see the styrofoam is still here, so that doesn't really degrade very well. Everything else is pretty well degraded, because you can see it's very, very dark and very whatever, so you can almost not distinguish what anything else is. But the thing is here also, this is water. And basically you have the water infiltration directly into the landfill. So that's a big no-no, obviously, because you're basically contaminating the whole water. It's near a stream, so you don't want to be building landfills that are close to streams because of this situation where the water just basically is infiltrating into the landfill, and of course it'll extract all of the
you don't want fish there.
No. And I won't say which country this is, but that's what they were doing actually, just a little bit further down, and we're going like, I don't think we're going to go to the restaurant down here.
Frozen fish?
No. Actually, what they ended up doing, because they ended up just actually, they wanted this land to be reused again. So actually they just they removed the waste from that whole area there. I think they incinerated as much as possible the waste. They did the water treatment because it's basically a very black water. So even if it's not highly toxic because it's over time, but black water is not very aesthetically pleasing. So they had to do all sorts of, probably an activated carbon type of treatment, I think, to remove the color as well. So this is definitely not a way to build landfills. And this is not a way to dress when you're visiting landfills either, because as you see, my shoes are just a horrible mess. They just went through the slopping of the mud and things like this. And the guy told me, he says, oh, by the way, we're going to the landfill first, and then you're doing your lecture. So I said, oh, gee, thank you for telling me that. So yeah, it just poured rain the day before, so it was like I had to basically, my shoes were like, yeah, they needed to build along there afterwards. Yeah, so this is basically a before shot of what they're doing with all the waste in your landfill. Actually, I don't know why, but it doesn't really smell there that much at all. And then, as you say, this is a place where they've basically allowed the vegetation basically to reclaim the land. So again, you cannot tell. So you see the landfill is still here, but this part is an old closed part of the landfill. So you can see that basically, again, they allowed it to go back to nature as much as possible, and it looked like just like part of the scenery. It's not.
Do they have to put a mesh or something and then?
Yeah, most likely, yeah. Because basically you have to build all the covers, you have to make sure that there's no gas being doing, and every once in a while, sometimes you might get more like basically compaction, because some of the waste might go a little bit further degrade, and then the other one might not. So you get sort of a difference in level sometimes. So they have to go back and fix it and maintain it every once in a while. So, and that obviously can cause sometimes some shearing of the covers. So for landfills, there's usually a whole set of layers of geotextiles and earth and grass and whatever that they use as covers for the landfills. So basically to protect, make sure that animals don't come and dig up everything and just break out everything, and also for weathering and for erosion purposes and things like that. Yeah. So, so this is another sort of a nice way of doing some if you have contaminated land, especially if it's like an organic contaminant, like if you have heavy metals, it's very difficult because, as you know, heavy metals don't degrade or anything like this. So you have to deal with with them in some way to stabilize them or to leach them out. So whereas if you have an organic, such as an oil or grease or solvents from, say, for example, from the dry cleaning industry, as you were mentioning before, what we can do is you can bring them to a facility such as this, and basically you allow the microorganisms that are in the soil to do the work, or you can add some microorganisms, so like a sludge or a compost or something like this that has a lot of microorganisms. You can mix it in with the earth. They use basically these backhoes basically to do a bit of a mixing, and then they cover it to make sure that you have no emissions going into the air. And then you can basically leave it for over time, maybe depending on what level of contamination. You can have like, it can be done in a month, or it could be done maybe in 2 or 3 months or whatever. So depending on what level.
So that's anaerobic?
It's aerobic. Okay. They put, actually they spray, they have like some piping, porous piping or whatever underneath. And they inject air into the bottom of this thing, and then which goes through the pile itself, and basically that will allow the organisms basically to do the degradation, and they might have to add a little bit of nutrients or a little bit of fertilizer or something like this, just a little bit. And so overall, it's fairly. You don't have to add too much, not many chemicals, not many materials. You allow the microorganisms to do the work for you, and then you can potentially the earth can be, depending on the level of contamination, you can bring it back to your site and use it for something else, or you can, you know.
Must be a big site.
Yeah, it is. They have many. This is actually in the East End, just behind the refineries. So they get obviously a lot of the soils and everything from the refineries, and but they get a lot of soil. Like if you're say for example, you have all of these gas stations that have been closed, and so often you have the leaking the tanks underneath. And so what will happen is that some of the leaking tanks would obviously cause the contamination in the ground. And then so now a company wants to come around and wants to develop the land for a condo project, which is like almost probably 90% of the cases around here. Yeah. And so then the land is contaminated, so then they have to do something about it. So so what they can do is they can extract the soil, so it gets it out of the place. They can use the ground for something else there, and then they can do the treatment over here, and it's not too costly. It's something like I think the guy was telling me it's something like about $45 a ton or something like this. So it's very inexpensive, and they can actually do it. See, the advantage is better. It costs less to do that than to send it to landfill, which is unfortunately often still the case.
Can they sell this after once it's decontaminated?
Yeah, they could. They could. Depends on the market, you know, like what they need it for and things like this, and what type of soil it is and so on. but everything is very tightly controlled, obviously, what goes in and goes out, so people have to track everything and so on. So that's what they're doing here. Here, they're starting to set up a way to treat the organic waste, say, for example, from the restaurants and things like this. So they want to, it's basically a composting system. And the difference with this one is it's like a mechanical system. So not like a lot of the composting is just like a pile or a ditch or basically a bin. In this case, what they're actually doing is they put it in one side and basically they do all the aeration and mixing. So it's kind of like a screw type of system. So it'll take, I don't know, maybe a few, maybe a month or something like this. And so it can go from one end to the other end. And by the time it reaches the other end, then you got your compost and it's done. So basically it's much better aeration system, it's much better mixing, so that's why it's done faster. So anytime you can optimize some of the processes like that, it's...
Is it hot in there?
Yeah, oh yeah, it will be, because composting, even these, actually even for these piles here, it comes in like what, 40, 50 degrees sometimes. And so this is the type, so for composting you need about 50, 55, something like that. Yeah. So this is a new thing that they're trying at this site, so they'll see if they can get a market for that and get people to bring it. Yeah, so we're talking about waste, lakes, rivers. There are also some other type of things that can be contaminated. There are not so many approaches that are used for treating lakes in situ. A lot of times you have to deal with what you have to deal with. So we've been trying to look at various systems because this is exactly what happens sometimes. You know, you have the streams, you have the overflows, you have even communities like up north where we've been doing some tests where they have the septic tanks are basically discharging into the lakes where you have various, runoff of the fertilizers from the ground and things like this or obviously from industries and so on. So this is often what happens. You have the emissions go and then they basically get into the lakes and rivers and then your poor fish eventually disappear like this because of the toxins and things like this. So of course they accumulate all of the toxins and so on. So these are some approaches that we've been using for some of our research. In I should have brought the little Japanese version and all the writing or whatever, but this was a barge basically that they renovated it and to made it like these sand filters. And so the idea was to remove all of the solids that were suspending and causing a lot of turbidity in the bays and the harbors here in Japan. So they were doing this as a test and making basically a large-scale test, basically, and doing this as kind of a bit of a biological part. So they're using these carbon fibers to do a bit of a pre-treatment on the organic materials because there was a little bit of oils in the water as well. And so they were running that to do like that. And then we did some small-scale tests because as you see, there's a lot of algae that grows. This apparently this was a pond in Japan where they were doing a lot of feeding of fish and so on. So people used to come, they'd had a fish in the little pond there and people would throw in stuff to feed the fish. So unfortunately it causes a lot of nutrients to accumulate in the ponds as well. So really you end up with something like this as the beginning. So this was the beginning and this was of course after the filtration. And so we just tried to do like an in situ type of filtration. So like a little floating filter basically. We did a very confined space to be able to do the test area. And we used the solar power to be able to generate the pumping of the water through the system. So really we were just kind of repumping the water and refiltering it as much as possible. So it's fairly successful. So as I was saying, these are some of the ways that the nutrients can get into the lakes and rivers. We had also done some tests in the Huron River, which is basically in the eastern townships near as you see, this is the Richelieu River, and it's kind of a tributary to the Richelieu River. And so this is kind of a very small river right at the source there, but gets bigger and bigger as you go along. And there are a lot of agricultural runoff there's a bit of an industry upstream, so there was a fair bit of lead and zinc and things like this that were getting into the river. And but there's a lot of erosion from the banks, and then what was happening also is that there were a lot of agricultural fields, so you get the barren agricultural fields, it would rain, they would just go, the culverts go just directly into the river. So the rivers, as you see, would tend to get very muddy, and of course they'd be full of all the nutrients and the phosphoruses and things like this that was from the rivers as well. We didn't measure pesticides because we didn't have the capability in our lab, but we were definitely doing studies with the suspended solids and the nutrient, nitrogen, phosphorus, and things like that. And also here is some of the little cyanobacteria. A few years ago, the citizens were starting to complain a lot about how much cyanobacteria was growing in their lakes. And then there were a lot of regulations, of course, in terms of the uses of soaps that didn't contain phosphorus, so they changed that. There were a lot of regulations now in terms of the discharges for the septic tanks, so that's also helped the situation a lot as well. And the other one was in terms of the riverbanks, the slopes, and the fertilizers that they were allowed to use on the slopes of the grass, basically. So you'd get a certain amount of runoff, obviously, of fertilizers and things like that. So they used to.
You're supposed to leave the grass around the lake.
Yeah,
that help?
yeah. So they tried to leave as much of the natural vegetation now around it instead of grass right to the. I think that they had to. There's a regulation in terms of the grass. I think had to be something like 6 feet away from the border of the lake and things like this. So all of these things have helped a lot. But you still get some situations like this because it's where it's shallow, or so in certain areas you might get sort of things like this. So we were doing some tests in this lake. I'll try to finish there soon. On this Lake Carroll, and basically it's kind of is what people mess up, sort of like that. Basically this lake was probably about half the size. The developer came along and says, "Oh, I have a brilliant idea. Let's make it a nice big lake, and then we can have all of these lakeside properties around it." Well, the thing is that the guy didn't know anything about biology or anything. There's no really input into the lake, and there's no output into the lake. So basically everything just stays in the lake. So by the middle of the summer, August, September, it is just one green. I don't think I have a really good picture of it, but it's just one green mess. It's awful. So we did a lot of sampling in the river, and well, this is the water actually from that same lake. And so we were trying to do develop a filtration system that basically just removes the phosphorus, because basically once you we have like a filter, a fibrous filter. You form the cake on the filter itself, and actually like this. You form the cake on it. So then basically if you have enough solids, the cake forms on it, and then the solids that becomes on the filter itself now will be able to absorb a lot of the phosphorus on it. The nitrogen, it doesn't remove that much, but the phosphorus, it does. It's quite efficient. So we were doing some small tests like that, and hopefully we can do some a little bit larger tests next summer. This is what we're aiming for doing. So, and this was another test thing that they were doing in Japan, basically looking at some of the organic materials, very high, and they were using basically a way to clean the bottom, was kind of like a resuspension, and then you have to do a whole series of materials there to basically you try to do these. Okay, let me try to do it. You do an air injection at the bottom of the sediments. It allows the sediments to resuspend. You pull out the very small sediments that are at the top, which have the higher contamination levels. And then, so basically it looks like that. So then you send it to a settling tank, which then gets rid of a lot of the water. You then get this amount of organic solids that are left, so you can show there's quite a bit. And so the thing is, if you can find a nice use for this, would be great, because otherwise it's just going to go into the landfill or some other thing. So if you can use it as a fertilizer or whatever, that would be good. So these are basically just the dewatering bags to remove the water, and they were oxidized a little bit, and then this is the solids that you get at the end. So yeah, so obviously if you can find a way to recycle the solids as much as possible, that would be great.
That must be heavy.
Yeah, oh yeah. It's a very clay material. It's very, very, very fine. So in terms of energy uses, this is a small project that we were doing in, this is our John Molson School of Business. So they have a solar panel on the side of the building here. So they've been kind of, it generates only a small percentage of the energy, but at least it's a pilot project basically to see how much energy and under what conditions that we can reduce. And this is a LEED building actually. Our building was not, which was built a couple of years before. Our building is just across, the engineering building is just across the street here. And unfortunately, they didn't let us do the full certification system for our building, but and so on. And this is a facility that people are using. It's like a small building, and they have some solar panels, so they're doing a little bit of research on looking at solar panels and the use of these solar panels there as a small test bed, basically. It's about 20 by 30 feet or something like that. So basically energy, obviously energy uses, energy efficiencies, looking at other alternative energy sources are really, obviously the way to go in the future. Conserving, reducing, like we have all sorts of systems like integrated into our building. If you're not in the room, the lights go out and all of these type of things. Yeah. So wind energy obviously is one of them. We've been doing some work on that. We've been also looking at doing osmotic energy, because basically if you use the differences in osmotic in the salt content in the oceans with meeting the freshwater content coming from the river, you can generate this osmotic pressure, which then can be used by membranes to be able then to generate energy, electrical energy. So this is one source also we're kind of starting to look at a little bit with Hydro-Quebec. So basically we want to be able to do a lot of work with these recycling. We've got to do the land development. So, which then, as I was saying, engineers really, really need to be able to communicate, because they got to be able to have, especially if we're doing these rehabilitation of land sites and things like this, there are a whole bunch of people that you got to talk with. So, and then if you're doing the renovation, rehabilitation, you have to be able to look at various systems. So we're also looking at trying to develop systems for actually indicating which, making all of how much emissions are produced by each remediation system. So not only is how you handle the system, but how are you actually doing the remediation also needs to be evaluated as well. So what kind of, got to do your project description, look at the various options. You got to select which are the most appropriate indicators to be able to do these sustainability evaluations, do the scoring, and then you can use these scoring systems as a way of deciding which is the best way to go. Because otherwise you do it by hearsay. So you develop these scoring systems with your clients and then with the other stakeholders. So all the people that are basically implicated in the project in some way, shape, or form. And so these are the different types of potential, or some of the types of indicators that you can use, like what kind of solids, what kind of energy uses, what kind of water uses, all of this type of stuff. So obviously our future challenges are to be able to, how do we design and do things like this? So we obviously need really good engineers like you guys in the future to, to design, construct, manage, and come up with develop new systems that can, thinking out of the box and so on. So we want to make sure that things don't compromise our future. And hopefully through initiatives like what we're trying to do, I'm setting up a new institute in water, energy, and sustainability. Basically trying to do these multidisciplinary research for engineers so that they'll be able to have all of the policy, economics, management aspects, as well as the society. So we're working together with all the faculties in the university and also with different universities as well. So hopefully this will be officially launched. Well, I got a nice grant, $1.6 million to do the training in it, and now, so some of it's for undergraduate training, and but mainly for graduate as well. So, and then as a final note, we have an open house this weekend. So if you want to hear more things about it, perfect timing. There's at our building downtown.
But ours is Sunday. So
yeah.
they're okay.
Yeah, exactly. So forget about McGill's, come to ours. I went to McGill, so I can say whatever I do. I know about McGill. So anyway, that's it. Thank you. Yeah.
First of all, thank you very much for Dr. Mulligan for this lovely presentation.
Thank you.
It's wonderful. I have 2 questions. Try to be brief. You had mentioned the pulp and paper industry as one that is sort of maybe self-regulating, cleaning up its act, it's using less coating chemicals and so on. What's the incentive for them? And sort of as a broader question, what is the best incentive for these companies? Is it purely government regulation, or is there a role of the market and technology advancement itself?
A little bit of both, I think. I mean, obviously the regulations will get them running in the fastest, but if you can find some way that can actually make economic sense for them, like if, say for example, if you have a process that they're going to need a lot less energy and things like this, I mean, that will help, obviously. And then if they can be able to develop some good products and things like this, some nice side products that can help them to, to close their loops and look after all the different wastes and things like this. Unfortunately, that's a lot of the problem, the waste. What is the market for that? And until we can get good products and good markets for these type of things, sometimes it really defeats all the lovely efforts for recycling that we have,
Okay. So. The other question, just quickly, you said that engineers nowadays are dealing as much with cultural and political issues as before. Is this incorporated in the sort of training that your engineers get at your university and at the university at large nowadays?
Yeah, we're trying to, we've done it slowly in some of the trying to increase some of the communication skills and so on. We have various things like internships and so on, where we have a co-op program. So these type of things can help. But in terms of this institute that I'm trying to set up, I'm really trying to focus on and trying to increase these social and skills in particular, because we'll be working very, very closely with the arts and science and with the political science and the management groups and things like this. So we're trying to.